everyone, and welcome to Algebra 2. This is section 6.6 on solving exponential and logarithmic equations. So we're going to start with some really straightforward problems that use the property of equality for exponential equations. So I think this property will make a lot of sense to you. It pretty much says that if you have 3 to the x is equal to 3 squared, what must x be equal to? And you can just see right away that in order for these two sides to be the same, the x has to be equal to the 2. That's what this is saying, that if you have b to the x is equal to b to the y, then x has to be equal to y. So when we see an equation like this, 5 to the 2x plus 1 is equal to 5 to the 3x minus 4, you can say to yourself, oh, well then 2x plus 1 must be equal to 3x minus 4. Subtracting 2x from both sides and then adding 4 to both sides, x is equal to 5. So you might want to stop this video and try the next 3 on your own, but of course I will do them for you. So number 2 doesn't have like bases, so you have to think to yourself, well, how can I make them alike? 4 is 2 squared, and 8 is 2 cubed. And then when you have a power to a power, you need to remember that you multiply them, not add them. And when you're multiplying this one, you need to remember to distribute. So this is 3x plus 3. But now that they have like bases, I can say 6x is equal to 3x plus 3. Subtracting 3x from both sides and then dividing by 3, I get x is equal to 1. On number 3, this already has a base 2, which I like because I know that I can make 32 into 2 to the 5th. Remember that a power to a power gets multiplied, and don't forget to distribute that 5 to both the x and the minus 1. Now that I have like bases, I can say 4x is equal to 5x minus 5. Adding the 5 to the other side and subtracting 4x gives me x is equal to 5. And the last one, 100 is equal to 10 squared. And this I can change to 10 to the negative 1. And that's how I'm going to give them like bases of 10. Again, a power to a power gets multiplied. And on this side, when you do it, don't forget to distribute. That's going to be negative x plus 3. So now I'm going to have positive 2x is equal to negative x plus 3. I add x to both sides, and that gives me x is equal to 1. Now, of course, these problems are very contrived. You're not always going to be able to make the bases the same. So the focus of our lesson is actually going to be what to do when you can't make the bases the same. And that is, we're going to take the log of both sides. Remember, fundamental principle of algebra. Whenever you do to one side of the equation, you have to do to the other. So if I have a base 2 as an exponent, then I can take the log base 2. And do you remember what that simplifies to? That's going to simplify to just x. Log base 2 and an exponential function of base 2 are inverses of each other, and so it cancels to just x. But if you take the log of one side, you have to take the log of the other. And so my final answer is x is equal to log base 2 of 7. So you can estimate that by plugging it into your calculator, and you'll get 2.807. But I will say that when you go to check this, if you're taking a test or something, if you plug 2.807 into here, it won't come out to be exactly 7 because this is an estimate. Now, as usual, before you take the log of both sides, you're going to want to simplify as much as possible. So I am going to subtract 4 from both sides first. 10 to the 2x minus 3 is equal to 17. And now that I have just a base, I can fix that, undo that by doing log base 10. Now it's true that you do not have to write log base 10 on both sides. It's understood that if you can't see the base, it is base 10. But some of you might want to write it just so that it helps you remember. I'm taking log base 10, and then I have an exponent base 10, and this becomes 2x minus 3. Sometimes students don't write these in the right spot, but let's assume you had lined paper here. That 10 should be a subscript, and this 10 should pretty much be on the line, and then this should be an exponent. But now when the log base 10 and the exponent with the base 10 cancels out, this 2x minus 3 is not still an exponent. It comes back down onto plane, shall we say. So I can add 3 to both sides, but it doesn't actually add to the log 17. This is not log 20. It's a number, and log 17 is a number. And then finally, x is equal to 3 plus log 17 all over 2. And you can just leave it just like that. You don't have to type it into your calculator to figure it out. Oh, if we were in class, I would say, who can make my day? Who can tell me what to do first? Hopefully you're answering that question anyway. The answer is clear fractions. These problems always look scarier. So just multiply both sides by 3. 3 times 2/3 is 3 over 1 times 2 over 3. Those 3's cancel and you just get 2. And then 3 times 1/3 is just 1. Already, doesn't that look like an easier problem? Just got to clear those fractions. So just as if you were isolating an x, you're going to isolate this e to the 4x. And I'm going to subtract 1 from both sides. I'm going to divide both sides by 2. And you can write 11 halves, or you can write 5.5, whichever you prefer. So what base undoes base e? Log base e. But of course, I wouldn't actually expect you to write that. Log base e is the same as natural log. So while you might choose to write it that way just to make sure you've got that correct, log base e is written as natural log. So log base e of e to the 4x just becomes 4x is equal to natural log, just to show you can do it this way too, natural log of 5.5. And my last step is to divide both sides by 4, and I get x is equal to the natural log of 5.5 all over 4. Which again, if you want to leave it like that, you can, or you can plug it into your calculator. Either answer is fine. So of course, now we're going to do it in reverse for logarithm functions. The same is true if you have log base b of x is equal to log base b of y, then certainly x must be equal to y. So if these are both log base 3's, then quite simply that means 5x minus 1 must be equal to x plus 7. Subtracting x from both sides and adding 1 to both sides, I get x is equal to 2. You should really try the next two on your own and then just fast forward through this video. But of course I will do them for you. Since the log bases are the same, I'm going to have x plus 3 is equal to 8x plus 17. I subtract x from both sides and subtract 17 from both sides, and I get x is equal to negative 2. And on the last one, I have natural log of 2x minus 1 is equal to the natural log of x plus 5, which means 2x minus 1 must be equal to x plus 5. Subtracting x from both sides and adding 1 to both sides, I get x is equal to 6. But like before, you're not always going to have a log base 5 on both sides or a log base 4 on both sides. So this time, we're going to exponentiate both sides. Okay, I'm going to write watch your form because a lot of people are a little bit lazy about this. This needs to be, if you're writing on lined paper, this needs to be 5 to the log base 5 of 3x plus 1 is equal to 5 to the 2. Remember what we said before? If you have 5 to the x is equal to 5 to the 2, that makes sense to you, right? X must be equal to 2. Well, now we're just starting in reverse. I'm starting with x is equal to 2, and I'm choosing to make both of those the two exponents with a base 5. Why would I do that? Because if I have a base 5 being raised to a log base 5 and exponential functions base 5 cancel each other out, and I just get 3x plus 1. On this side, the 5 doesn't cancel. I added that to both sides, but on this side, I need it is equal to 25. So now I can rewrite this as 3x is equal to 24, x is equal to 8. So I know it looks a little funny, but I really want to make sure you're seeing these lines. This is 4 to the log base 4 of x plus 3 is equal to 4 to the 2. If you're not clear in your work, it'll look like 4 times 2, and you'll accidentally write 8 here. But this is 16 on this side. And on this side, it's just x plus 3. I'm subtracting 3 from both sides. I get x is equal to 13. Next one, 5 to the log base 5. That's how you're going to cancel out a log. So just to go back really quick, if you have an exponent, if your x is stuck in the exponent, you're going to take the log of both sides, and you're going to decide what log based on this base, because log base 2 of 2 to the x is just x. But conversely, if you're stuck with a log and you're trying to get rid of the log, then you're going to exponentiate 5 to the. So now on this side, I get x minus 4 is equal to 5 to the 2, which is 25. X is equal to, add 4 to both sides, 29. Because the domain of a logarithmic function generally does not include all real numbers, you need to make sure that you check for extraneous solutions. And of course, you're going to find those in the next couple as examples. But first, the more important thing is that I really want you to know that you cannot exponentiate individual terms. So let's just say 1 plus 2 is equal to 3. Agreed? But is 2 to the 1 plus 2 to the 2 equal to 2 to the third? No. This would be 2 plus 4 is equal to 8? Definitely not. Okay? So do not exponentiate individual terms. Okay? Very, very common mistake. I'm always trying to point out the common mistakes. So you might be thinking, well, then what am I supposed to do? You're supposed to condense first. That's what we're going to do. So you might remember from last section, condensing, which is when you rewrite this as log of 5x times x minus 1 is equal to 2. Or to simplify it even further, log of 5x squared minus 5x is equal to 2. Now that you have a single log, now you can raise the power. The power is 10. If you want, you could fill it in just to make sure you see it. So this is going to be 10 to the log base 10 of 5x squared minus 5x. And whatever you do to one side, you have to do to the other. So this is 10 to the 2. On this side, an exponential base 10 with a log base 10 cancels each other out, and this side becomes 5x squared minus 5x is equal to 100. I see an x squared in my equation. What do? I set it equal to 0 and factor. That's what you always do when you have an x squared or higher in your equation. So 5x squared minus 5x minus 100 is equal to 0. And what kind of factoring should you always do first? Factor out first. It's not that it's not factorable at this stage. It's just so much harder to think of the factors. But now that I've written it like that, it's easy. It's got to be x and x. And your first two choices would be 4 and 5, 4 and 5, and the inners and the outers mean that you're going to want that to be negative and that to be positive. So remember, this does not mean that x is equal to 0. You have 3 things that are equal to 0, 3 factors. Which of those factors is causing the answer to be 0? Not this one. 5 will never make the answer equal to 0. So instead, it must either be that x plus 4 is equal to 0 or x minus 5 is equal to 0. But 5 is never equal to 0. So my 2 answers are -4 or +5. But if you check that, if you put a -4 in here, you'll be trying to take the log of -20, and you can't take the log of a negative number. All right, second warning of the day. The first one was do not exponentiate individual terms. And the second one is don't assume that the negative answer is the problem. If you had log of x plus 8, then x is equal to -4 would have been fine. So don't assume just because you get a negative answer that needs to be crossed out. And similarly, the 5 could have been a problem. If you had log of 3 minus x, then if x had been 5, you'd be taking the log of a negative number. So be really careful that you don't just look at the 2 answers and cross off the negative one. You just have to plug it in to make sure in the problem you're not taking the log of a negative number. All right, you might want to try this next one on your own. I will tell you that the answer is 8, but of course we'll do it together. So my first step is to condense log base 2 of x squared minus 7x is equal to 3. I'm going to write that as 2 to the log base 2 of x squared minus 7x is equal to 2 to the 3, which gives me x squared minus 7x is equal to 8. So another common error, I'm not really sure why this is, but a very common error is to only exponentiate this side. People literally just get rid of the log and write x squared minus 7x. You have to do it to both sides to keep it true and correct. I see an x squared in my equation. What do? I set it equal to 0 and I factor. After I get my answers, I always check for extraneous solutions. And in this one, it happens to be that, again, the negative doesn't work, but you cannot count on that being true all the time. Sometimes you can in Algebra 2, but certainly by the time you get to pre-calculus and calculus, that will not be the case. All right, the answer to number 3, if you're trying these on your own, is 4. There is no solution to number 4, and the answer to number 5 is e to the 12th over 10. Hopefully you're trying a couple of these on your own. First step is to condense. This is log base 6 of x squared plus 5x. Notice I have parentheses there. If I didn't, it would look just like log base 6 of x squared, and then 5x would not be considered part of the log. It would just be this plus 5x. So those parentheses are really important. On the other side, I still just have 2. I'm going to do 6 to the, this is called exponentiating. I'm going to exponentiate both sides using a base of 6. On this side, my base 6 for my exponent and my base 6 for my logarithm cancel each other out. And I get x squared plus 5x is equal to 36. I see an x squared in my equation. What do? I set it equal to 0 and I factor. My 2 answers are that x is either equal to -9 or 4. If you plug the 4 in, you have no problem with the negative, but if you plug in the -9, this becomes log base 6 of -4, which is not allowed. So my only answer is 4. So the next one's a little trickier. We've got a minus there. Do you remember what that does? that's going to condense to division. So I'm going to have natural log of x minus 1 over x plus 1. And now you actually don't need parentheses because they're joined by the division. This is actually already 1 to 1. It's already a natural log of both sides. So you could literally just skip to x plus 5 is equal to x minus 1 over x plus 1. However, if you didn't think of that and you're like, oh, I exponentiated, I did the e, that's okay. Look, I can do that step and it's still going to give you the exact same next step. You'll just have done an extra one, so it's okay. I'm going to clear this fraction. Always clear your fractions. It will make your life so much better. So on this side, I get x squared foiling out plus 6x plus 5. And on this side, I just get x minus 1. I see an x squared in my equation. What do? I set it equal to 0, and I factor. X plus 2 times x plus 3 is equal to 0. X is either equal to negative 2 or negative 3. And unfortunately, both of those answers will cause you to get no solution. That's the symbol for no solution. Now, I will just show you a little alternative here I've had some students do in the past, which is they don't want to deal with the fraction, so they've actually moved it to the other side first. They've changed it to natural log of x plus 5 plus natural log of x plus 1 is equal to natural log of x minus 1. Very, very clever. And then they just had to multiply those two. X squared plus 6x plus 5 is equal to natural log of x minus 1. And then that put them right back down here at this step, that this must be equal to this. So interesting concept there. If you can think of that, that's fantastic. And number 5. So we're back to an example where we're going to just get this natural log of x all by itself. That's what I'm looking to isolate. So I'm going to add 3 to both sides. That gives me 10. Natural log of 100x is equal to 120. Natural log of 100 and x dividing both sides by 10 is 12. I undo a natural log with an e. That's its inverse. And if you look, if you ever forget that, they're both on your calculator in the same spot. That's how you can know that they go together. And then that's going to give me 100x is equal to e to the 12th. And if you divide both sides by 100, you're going to get e to the 12th over 100. So on my calculator, my e button, remember, is next to the 4. But this is e to the 12th. I go over with the arrow key to make sure I'm not part of the exponent anymore. Over 100. I didn't bother to use the fraction key. Just the division symbol will work here. So you could have written your answer as 1,627.547914. However, if you want to check that answer and you've rounded to 0.548, it's not going to check exactly right. So what you can do is you can use this store button, store as X, hit enter, and it's like, I got it. Your calculator's saying I got it. And then just type it in. 10 natural log of 100, and you can say X now, instead of having to type that number in. Now remember to end your parentheses, even though it's not in the original problem, minus 3, and there you go. 117. You can be completely confident that you got it right. So let's do a couple word problems. Newton's law of cooling states that the temperature T of a cooling substance at time t in minutes can be modeled by this equation. TO is going to stand for the initial, I like to think of it as original temperature. TR is going to be the room temperature. And R is actually just a constant that represents the cooling rate of the substance. So some substances might cool faster than others. Our problem is going to be dealing with a stew. So when you take the stew off the stove, its temperature is 212 degrees, and we're going to put it in a room that's 70 degrees. So stew specifically has an R value of 0.046. And we're going to use that to calculate how long it will take to cool the stew to a serving temperature of 100. So I want it to come out to be 100 degrees. My original temperature is 212. The room temperature is 70. And I'm going to multiply that by e to the negative 0.046. Make sure you get that correct. And then time, that's what I don't know. I want to know how long it's going to take, plus TR again. I know we've already used that. It's in the formula twice. So back at the beginning of the chapter, when we did problems like this, you plugged this in as y1 and this in as y2, and then you can use your intersect feature to find the answer. And you still may choose to do that. You may choose to look at it and say, well, it's not that hard to make a window. I know that I want my y min, the temperatures starting at 212. So to see the beginning of the graph, I might want to start up at 220 degrees, and I need it to go down to at least 100. But you could even just go all the way back down to 0. And for your x min and your x max, it's number of minutes. So it's not going to be negative minutes. And you might say, I don't know, how long could it take? Could it take more than 30 minutes? You could start at 30. It might be significantly less than that or more than that. But it is a little bit of figuring out, even when you just do y1 and y2, exactly how to do it. So now you're going to finally have a choice. Now, if you want to, you can solve it algebraically. So I subtract 70 from both sides, and I get 30 is equal to, and sorry, getting out my calculator here, 212 minus 70. So I get 142 e to the negative 0.046 t. 30 divided by 142 is 0. Okay, now this is tricky. I'm going to write 0.211, but don't actually round. I do not want to actually round. This is just what I'm writing on my paper, but I'm going to leave this number on my calculator. That's super important that you don't round mid-problem. Is equal to e to the negative 0.046 t. Now I'm going to take the natural log of both sides. And the way you can do that on your calculator is to say, hit the natural log button and then hit second answer. So I'll put it like this. Natural log second, doesn't want to write that small, second answer. That's how you can get your calculator to keep that same number without even storing it. Is equal to the natural log of e to the negative 0.046 t. That's going to give me negative 1.554. Again, I'm still not rounding anything, okay? Again, don't actually round. I'm just showing you the numbers on the paper so that you can see them, but you should be doing this on your calculator without rounding. Is equal to negative 0.046 t. Now I'm going to hit divide. The number's already on my calculator. 0.046 divided by negative 0.046 divided by negative 0.046, and I get t is equal to 33.796. And now you can round. What are we in? Minutes. Okay, so about 34 minutes to do that. So would my X max have worked? No, but you probably would have seen that they were about to intersect and maybe just moved that up to 40. So doing it on your calculator would not be a terrible way, and I will accept that. However, just to note on a test, if you just write the equation and then get the wrong answer, I can't find your mistake. I'll assume you've done it on the calculator, and then I won't be able to give you partial credit. So sometimes it's worth doing on your calculator, and sometimes it's worth showing me out by hand. All right, next word problem. So the moment magnitude m of an earthquake that releases energy E in ergs can be modeled by the given equation. On May 22nd, 1960, a powerful earthquake took place in Chile. It had a moment magnitude of 9.5. How much energy did this earthquake release? So it's mostly knowing where to put things. So this 9.5 is going to go over here, is equal to 0.291 natural log of E plus 1.17. So again, you can do this as y1 and y2 on your calculator and come up with what you think is a reasonable window to see that, or you can just start doing it algebraically. So subtracting 1.17 from both sides, I get 8.33 is equal to 0.291 natural log. By the way, this natural log and this E don't cancel. It is true that natural log and E cancel each other out. But this is a capital E, it stands for ergs. And then I divide both sides by 0.291. And I get, all right, so again, I'm going to write down 28.625, but I'm going to leave that whole number on my calculator. And then I'm going to do e to the 28.625 is equal to e to the natural log of e. So since this number's already on my calculator, I can do e to the answer, and that's how you can use that. So I get 2.703, but then if you keep looking at the number after all the other digits, it's going to say E12. You need to be able to interpret that. That's your calculator's way of writing 2.703 times 10 to the 12th. It means it's a huge number, right? It means it's 2.703, 1, 2, 3, 1, 2, 3. There's going to be 12 of them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's how many ergs it is. It's huge. But you guys may not use the notation E12. That's your calculator's notation. You can either write it out, which I doubt you want to do, or you can just leave it in what we call scientific notation. Okay, last two. These are different because they have a greater than or less than symbol and an equality symbol, but we still solve them the same way. I'm going to take the log base 3. Whenever you're trying to undo an exponential function, you use a log to do it. And you always have to do the same thing to both sides. So log base 3 of 20. That gives me x is less than 2.727. It's just that easy, so don't let the inequality throw you. Number 2. So first we did one with an exponential, now we do one with a log. How do you undo a log? You just need to give it the same base. So this is log base 10 of x, so I'm going to exponentiate both sides with a base 10. So 10 to the log base 10 of x is equal to 10 to the 2, which of course is just 10 squared, so we get 100. And then this log base 10 cancels with this base 10, and we just get x. And it was less than or equal to. I'm going to put that back in. Now this is where you have to watch out. Remember, you can't take the log of a negative number. So on your own, you're going to have to think to put this extra x is greater than 0 in. If you recall the graph of a log, it looks like this. It never touches 0. It's never negative. So this will actually only be true if x is less than 100, less than or equal to 100, but it does have to be greater than 0. Unfortunately, your homework does not practice any of these. So there is an extra one of these to practice. Number 12 on the extra practice is like this, but unfortunately your homework does not include any of them. So it's going to be up to you to remember to watch out. All right, that is it for section 6.6. Have a great day.